Hi, welcome to week number 9, shear force and bending moment equations and diagrams, right? We will investigate in this week how to get the variation of internal forces not at a single point, like we have been doing. We choose a point, we cut through it, we expose internal forces, we solve for them using the equilibrium equations. But rather, we will develop equations that will give us the variation of internal forces along the length of a member, right? Not at a single point, but an equation that will allow us to get, or a set of equations that will allow us to find the internal forces at any location we want. So the first, we will investigate two methods. We will use two methods. The first one is the equation method, and then the second is the graphical or quick and easy, also so-called quick and easy method. So the first method we'll tackle is the equation method. So shear and moment equations and diagrams, right? Thus far we have looked at the calculation of internal forces at specific points. That's what we have been doing. Example, right? We calculate the bending moment or the shear at the mid-span of a beam, right? So we have so we have like beam like this, and then some load over here, and then we decide to cut, right? And then investigate what are the forces. This is A, B, right? What are the internal forces at point C, right? So in some cases, right, those related to design, it's very important to know the internal forces not at a single point, but at any point, right? At any point. So in those cases, we'll need to evaluate the internal forces at many locations, right? And then it's important to develop a systematic method to do so. And why would we need to know the variation of internal forces in a member, right? Now, this is a very important problem to solve, right? And this is the method that we'll discuss today. So, we'll use it mostly in beams, right? They appear in many types of structures, right? Floor joists used in house construction, main spans in aircraft, wings, and many others. These elements, beams that we have been solving, they have their dominant loading perpendicular to the long axis of the member, right? So these are the cases that we'll be discussing, right? It's exactly the same as we did with reactions. In previous examples, we chose a location along the beam to calculate the internal forces, the middle of the beam, point B, point C. Now, at each section for analysis, we cut through the member, we introduce the internal forces exposed at the cut, and we solve for them using equilibrium equations. Now, if we were asked to do this at 10 points along the beam, right, it will be a very tedious process, right? It will be very time consuming to find internal forces at many locations in the beam. Now, but we do need to know the variation of the internal forces, right, along the entire length, not at many points, but at the entire length, because this allows us to solve critical problems in design of these members. For example, we have to choose a member with enough strength and stiffness. And how can we do that if we are missing that? Maybe not at the middle of the beam, but maybe close to the supports. We have the weak spots, right? So, so this is the second aspect, right? Identification of critical regions, weak spots, regions of the beam or the member that have very high internal forces. If we cannot identify or we cannot find them, right, we are going to potentially have a weak spot in our beam, or maybe we are using too much material, right? And then the beam is going to be very expensive, very safe, but very expensive. So maybe there are regions in that beam that do not need that much material. So we have to identify those regions in which the internal forces are low, right? So we can optimize, right? So this last problem is optimization, right? Removing material that we don't actually need, and probably add it to those regions that need it, right? The weak spots, right? So all this requires a method that allows us to get the internal forces, right? Or to know the variation of internal forces along the member, right? In a very quick example, I can tell you that, right? If we just do it point by point, we can see that the internal forces are not constant, right? Are not constant along the length. They change, right? Their value changes when we move from point to point. And then I just create figures here to illustrate that point and show you that the internal forces will be changing, right, along the member. So how do we achieve this? Well, probably you are guessing what is the process we are going to follow, right? Now, if in the past we we chose our section, we said, well, calculate the internal forces at 1 meter from the support, right? Now we're going to calculate the internal forces at a distance x, right? A general location x. So spoiler alert, we will do exactly the same process, right? But instead of one specific distance, right, we will do it for a general location x, and we will do exactly the same. We'll expose the internal forces, and then we apply the equilibrium equations, and what we will get are internal forces, but they will be in terms of x. So we will get equations instead of numerical values, just scalars. We would get equations that we just can evaluate for different values of x, right? Different values of x. Now, something really important, right? Something really important to take into account is that we cannot just choose or do this just once. For example, if I consider this example and I choose a position x to start my my equations, right? Take a look at this load, right, on top. Right? Take a look at, let me use probably a different color, maybe blue. Take a look at this load, right, on top. It's clearly a discontinuity on my beam, right? I can define, right, I can very, very well define a segment just before the load, right? Just before the load. I can define a segment for which my variable x here below is going to be valid, right? But after the load, right, I have to reapply my my method, right? So this is another segment. So every time you have a load or a reaction, or the load changes, you have another segment, and you have to define a different x, right? So your equations at the end, right, you're going to have brackets of applicability, right? So this equation will be valid for this range, right? And in this range, in this other range, in the next segment, this set of equations are going to be the ones that you have to use. And in this other segment, this is your set of equations that you will be using. So every time the load changes, or you have a reaction, or you have a new load, you have to define a different segment. So for example, this is my first segment, right? And then my my variable x is defined from the origin, right, to some point, to some arbitrary point just before the load, right? Just before the load. And then the next segment, right, I can oh, actually very nice, right? I can start, let's start defining our equations, right? So before we jump into the next segment. Okay, so let's put it in practice. Let's see what happens. I have defined my segment x, right? And it's valid for x, right? X bigger than 0, right? And less than 3 meters. So our first set of equation is valid for the range 0 to 3 meters. And I have exposed my internal forces that you see here. I'm using, of course, my convention of signs. And just as a reminder, right, for forces in this right-hand side, right, in this right-hand side face, I'm using these forces in the right-hand side of the convention of signs. So I have drawn my internal forces, right, like this, right. So I have a normal force N1x, I have shear force V1 in x, and I have moment in x at the cut. So I'm going to apply my equilibrium equations, right? Sum of forces in x equal to 0, right? And then there are no normal forces to see, so normal force 1 in x is equal to 0, right? That's my first function. What about sum of forces in y equal to 0? Whatever goes up is positive, so I have the reaction, right? The reaction 1 goes up, and then minus the shear force in x, and then there is nothing else, so this is equal to 0, so my shear is equal to 1. And what about the moment? Well, sum of moments at the cut equal to 0, counterclockwise is positive. I have the moment caused by the reaction, right? It causes clockwise moment about the cut, so negative 1 times the moment arm is equal to x, so it's minus 1 times x, right? There is no other reaction that causes moment, and then I have counterclockwise moment, so m1x positive equal to 0, so the moment at x in the first cut is equal to x. These are my three equations for the internal forces, and these are valid for the first segment. So let me clean up this, and then we can see my three equations for the first segment. So now we are going to jump into the next segment, right? So this segment over here, right? This segment over there, right? Because of that 3 kilonewton load, we have now to jump into the next segment, and it's here. And I have defined, you see, my x value from the load to any point before the support, right? Now this cut, you see, you have to notice that it doesn't account for the force in the support, right? The cut is just before the support, so I don't have to worry about the reaction at the support. So something really important, right? So I have defined my internal forces, right? Again, using my convention of signs. And I'm going to apply equilibrium equations, right? Same thing as before. I think the most important part that you have to, or I am going to ask you to notice, right, is how, right? And this is one of the trickiest parts, and it comes with practice. You have to locate each force, right, with respect to the cut. For example, right, it's important that I have located my force of 3 kilonewtons, right, and I have provided a location for it equal to x minus 2, right? So x minus 2 meters, right? X minus 2 meters. That is the location of that force. So if right, if this is 2 meters and this is x down here, so that distance is x minus 2, right? So locating the forces with respect to x is something that we have to get used to do, right? Because it's going to be quite useful. So let's apply our equilibrium equations. So sum of force in x equal to 0. Normal force is again equal to 0 because there is no other horizontal force. Sum of forces in y equal to 0. Whatever goes up is positive. I have a reaction of 1 being positive. I have a force of 3 kilonewtons being negative. And I have the shear force at the cut going down, right? So it's minus V2 in x equal to 0. I can solve for the shear, and the shear is equal to minus 2 kilonewtons. What about the moment? Sum of moments at the cut equal to 0. clockwise is positive, and I have now the moment caused by the reaction in the left hand side times x, right? That's the distance to the cut, creates clockwise moment about the cut, so it's negative minus 1 times x, plus the moment from this load of 3 and causes counterclockwise moment about the cut, so positive. And then distance to the cut is x minus 2, so positive 3 kilonewtons times x minus 2. And then plus the moment at the cut, which is m2 positive in x because it's counterclockwise, is equal to 0. I can solve for the moment, and the moment is minus 2x plus 6, right? That is the moment. So I have obtained one set of equations for the first segment, and then I have another set of equations for the next segment, and then I can use these equations to calculate the variation of the internal forces. Right. So I just got functions for shear, for moment, and for axial force, right? And the x is measured from a location, right? From the origin, right, to the point in which the load changes, and so on and so forth. So what good are these equations, you may be asking, right? They don't give us a number. Well, they don't give us a number, but we can use to plot the equations. So we'll be plotting these equations, right? The equations themselves offer a lot of information, but nothing like having a graph, right? Nothing like having a graph. So that's what we are going to do. The graph of shear force, right, is going to be called a shear force diagram, or SFD, shear force diagram. And the graph of moment is going to be the bending moment diagram, or BMD. Right? Beams usually don't have a lot of normal force, right? But if you plotted the variation of axial load, this will be the normal force diagram, right? The normal, or the axial force, normal force, the diagram. Right? So yeah. So but these two, right? Shear and moment are the ones that are most usual, right? Now the graphs are really powerful because they greatly simplify the process of finding minimum or maximum values of shear and moment, right? Or specific values as needed. We don't have to derive ones to find the minimum of the shear or the maximum, right? And then derive again to just make sure that it is indeed a maximum or a minimum, right? If we just plot it, we can get the information immediately. So for example, here I have plotted the sets of equations for shear and moment for the two segments for the beam that we just solved. And we see here, right, these are my equations in the first segment, right? So here, this guy and this guy, right? You can see that the shear is constant, equal to 1 in the first segment, right? So this guy is constant. And then it's also constant in the next segment, constant and equal to minus 2, right? And then what about the moment? Well, the moment is equal to x in the first segment, and then the moment is equal to minus 2x plus 6 in the next segment, right? In the next segment. So you may remember that we also had a variation of axial load, but that was 0, right? So we don't usually plot the normal force, right? Because in many cases we won't have, right? But this is not in all cases, right? In some beams, for different types of loading, you will have normal force, right? So things to notice, right? We have seen that we have been using free body diagrams to solve for the internal forces, right? And we have to be careful, right, to identify the segments, right? It's important. So these segments will change, right, with load when the load pattern changes, when you have supports, etc., right? So you will have different sets of equations, right? You will have different sets of equations in different parts of the beam. So one quick example, right? One quick example for this one. How many segments do you see? So quick trivia, right? Quick trivia. So for example, myself, I see one segment here, and then another segment here, and then another segment over here, right? And then if you ask me, okay, where will you have your cut, right? It is a bit before the load changes, right? A bit before the load changes. Let me just make sure this load is not lost. It's something like that. Right, so just highlighting the fact that I have loads here. So your X is defined just a bit, right? For example, for the first segment, you will define your first X just a bit before the load changes. So this is the first X. And what about the second cut? Well, just a bit before the next cut. That will be your second X. Right? And then what about the third? Well, it's a bit before the support, right? Because that's where the load changes. So this is your third X segment. So it's just a bit before, right? It's just a bit before the load changes, right? So and then we expect, of course, that the values of shear and moment will be different for each new free body diagram or each segment, right? So we divided that beam into several segments, right, where the external loading changed, and we include the reactions here on external loads, right? So either when the external loading changes, that includes reactions. That's when the free body diagram changes. So what about this beam? Right? What about this beam? How many segments can you see? Right? So I see two supports over here. Right? Two supports. I see some loading. Right? I see some loading. So for example, this is a load, and here is of course a load. So how many segments? How would you divide this beam into segments, right? Let's use green in this case. So myself, I see one segment, another segment, right? Another segment, 3, another segment, 4, and then another segment, 5, and 6. Six segments, right, for this particular. So let's see. Yeah, 1, 2, 3, 4, 5, 6, 6 segments, right? And then remember, we define your X variable just a bit before in your segment, just a bit before the load changes, right? So once your functions for M and B are defined in each segment, the maximum values and the minimum, right, for internal forces are easily found, right? Of course, you have to plot these equations to see the variation, right? And as an engineer, you're interested in these maximum and minimum values for shear and moment and axial load, because you want to create safe and economical designs, right? For the safe design, you are interested in the maximum values. And then for the economical design, you are interested in the minimum values. Right? Maximum values, because then you need to add, right? Need to add more material or stronger material. Right? For minimum values, maybe you can remove some of the material, so you can make it cheaper, your member, right? Or you can use a weaker material, right? So for economical design. So you're interested in the maximum and minimum values. So just to summarize, what is the analytical process to plot the shear force diagram and the bending moment diagram? Well, right, this is not a recipe, right? Again, it's not a recipe. It requires practice, right? You'll become good at this only through practice. So we draw the free body diagram for the entire member, and we solve for the external reactions, right? We have to start with the reactions, otherwise we cannot find the internal forces, right? we draw a free body diagram for the complete beam, right, just to solve for the reactions, showing the unknown reactions, both forces and moments. We write the equations of equilibrium, we solve the equations of equilibrium for the reactions, we identify regions on my member, right, and then we find the shear force and bending moment functions for each segment, right? Now, for each segment, we have to analyze, right, each segment as a free body diagram, right, and obtain the equations. Remember to plot your internal forces according to the convention, right? To the convention. It's really, really important that that figure goes with you everywhere, right? Goes with you everywhere. So so we write the equation of equilibrium for each segment. We some moments about the cut end, some forces, right? And then we obtain the equations for shear and moment, right? We set up axes, right, for shear versus length or versus distance, and also for the moment, right? And then we usually plot the shear force diagram and the bending moment diagram underneath the beam. So we can take a look at loads and geometry on top, and then right, reactions here, and then shear here, and then moment in this diagram, right? So in a very neat, using neat drawings, we plot these diagrams one below the other, right? One below the other. So in the next topic, right, and we plot, of course, our functions. In the next topic, we'll be doing some examples on the equation method. So see you there. See you on the examples. So.